figure out how can you decide if a molecule is polar or non-polar. And if you have a polar molecule, it means two things. You have to have polar bonds and it has to be asymmetrical. So it has to not be symmetrical and have a polar bond. We'll see what both of those are. And what a polar molecule does, what a polar molecule is, it's a molecule that has a partial positive charge on one side and a partial negative charge on the other. So it would be like the one we know the most of, water. So water has a tetrahedral electronic shape because there's four things repelling. So four things makes it a tetrahedral electronic shape. And it's bent because we can only see these, the oxygen and the two hydrogens. Oxygen's more electronegative than hydrogen, so the electrons get pulled closer to the oxygen. So if I were to draw this, it'd be like, we'll put the pair in between the oxygen and hydrogen closer to the oxygen than they are to the hydrogen. So you have these somewhat bare protons down here, making it partially positive, and then more electrons up here, so it'll be partially negative on the top. So it has two poles. It's a polar molecule. You might ask, why do we care? We care. We care because if we did not have polar molecules and we're still built out of everything we're built of, it would be horrible. All your phospholipid bilayers, all your membranes, those are all held together because you have your polar heads and your non-polar tails kind of sticking together to keep polar on one side and non-polar on the others. Anyways, it's held together by polarity. So all your cell walls would just fall open, cell contents would come out. Water that we're mostly made of water, all the water would just evaporate because water is held together to be a liquid because water is attracted to itself, would no longer stick around in you. That's bad. In fact, your DNA, the two strands are held together by polar bonds. It's hydrogen bonding that occurs. So your DNA would just fall apart, and so you can program anything in your body. So care. Ooh, the other reason we care is because I have no idea if you can see this. None. The other reason we care is because we can do this. So polar molecules act like magnets. They're charged. See, maybe. So they're charged. So if I just build up a little bit of charge on this balloon, then I have, let's see if I do hold this, maybe you'll be able to see the solution a little bit better. And I've got this purple solution that's going to come out of here and hopefully not spill over everything. It's just water, purple water, make it look cooler. Hopefully you can see it better. So I got this charged balloon, and I just bring this closer and farther away, and oh my gosh, it's so exciting. If you can see the very bottom, it just barely moves. Oh, it barely moves. It's pretty pathetic. More static. So, maybe you can hear it. Did you hear that? It moves closer to the balloon. Okay, because it's charged. So the charged water is attracted to the static charge on the balloon. Wow. That and we get to live. So, two reasons. Been at school too long. So, let's see. What polar means? Polar means having two poles. A positive pole and a negative pole. Positive pole where you're missing the electrons, and a negative pole where the electrons are gathered together because electrons are negative. And a polar bond, it's a bond with two poles. You'll have a negative end and a positive end. What causes a polar bond is going to be one atom is more electronegative, and that means it attracts its electrons more. It pulls the electrons towards it in a bond. So we saw that in oxygen and hydrogen. Oxygen's more electronegative, so it draws the electrons closer to the oxygen than to the hydrogen. It's because oxygen has more protons attracting than the hydrogen does, even though the hydrogen has less shielding. So, anyways, the electrons get pulled more to one atom than the other, so you have a negative end, and then you'll have a more positive end. So that's the polar bond. The reason a polar molecule needs to be asymmetrical and have polar bonds is the polar bonds are going to make the negative positive areas, but they could cancel out. For example, you could have carbon dioxide. Oxygen is very electronegative. Fluorine's the most electronegative. It's in the that top corner, kind of, the periodic table. It's the most electronegative atom we have. There we go. Hey. So oxygen's really close to the fluorine, so it's going to be super electronegative. So when we have carbon dioxide, the electrons are closer to the oxygen than they are to the carbon. So you can say, here, there's my Lewis dot structure. You can say that I'll have a partial negative on this side. Carbon will be partially positive because its electrons are being pulled away from it. It's just left with extra protons, or the same number of protons it had that's not so close to its electrons anymore. And oxygen's also partially negative. So those two poles cancel each other out. You know, one pulling this way, one pulling this way. Right? So when you're caught between two things, that kind of cancels out. So symmetrical molecules end up being nonpolar. What you need is something like the water situation. Let's go back and look at that. The water situation where oxygen's pulling the electrons towards it, and over here as well. So overall you have this up and to the right, up and to the left. So overall your vector is like, that's straight up. So you end up with negative on one side, positive on the other. So the thing you have to do, check to see if you have a polar bond, and for the most part, anytime you have two different atoms, it's a polar bond. Carbon and hydrogen have very, very similar electronegativities, so they're not going to be polar. And we will just think about these are the most electronegative, and it decreases as we go down. So as long as we don't have anything that's like here and here all the way down, we're going to consider it polar. For the most part, unless you have identical atoms, or if you have carbon and hydrogen, it's going to be a polar bond. They're two different atoms. So polar bonds and asymmetrical. So those poles don't cancel out. Let's try. So before we do one, let's see which molecules are polar and which ones aren't. I love chemibear.com. Man, it's made my life easier. Not that we're always just looking for easy, but thank you. When you're looking at the shapes, this is really quick. You guys can look at some models and think about why is it polar, why is it not. But when you have a trigonal planar molecule, it's flat, 120 degrees all the way around. This is symmetrical. So if all three of these things are the same, it's nonpolar. By the way, I would pause, get out the shape sheet, so that I could mark on my shape sheet which ones are polar, which ones aren't. Okay, so this is a symmetrical when all three things on the outside are the same, so it's nonpolar. Here you can see this electron pair won't balance these things out. So if you have the bent shape, aka V, aka nonlinear, it's going to be a polar shape. Then we go to all the tetrahedral electronic shapes. If you have a tetrahedral, it is symmetrical. So it's the same all the way around. Oops, that's identical. So since it's the same all the way around, if you have the same four atoms, it is going to be nonpolar, it's symmetrical. This guy, this electron pair on top, makes it asymmetrical. It's bent, so it's no longer like this trigonal planar. And it has an electron pair here, so it wouldn't be canceling out the other guys. So this guy is not symmetrical, so that means if you have a pyramidal, you're going to have a polar molecule. Same thing with this guy, it's the shape of water, bent. So it's not going to be symmetrical, it is polar. For trigonal bipyramidal, you have a trigonal planar right here, and then a line. Both the line and the trigonal planar are symmetrical shapes, so just putting them together, it's still a symmetrical shape. So if you have all five the same, or even three the same, two the same, it is a symmetrical molecule, so it's nonpolar. As soon as you remove one thing, which you're going to put an electron pair on the equatorial electrons, it's no longer symmetrical. You can see that the top is not like the bottom. So with one electron pair, it's going to be polar. With two electron pairs, it is still polar. With three electron pairs, you're down to a line, and it ends up being nonpolar again because it is symmetrical. Then, with octahedral, when we have 6 things attached, these are all 90 degrees all the way around. So this guy is symmetrical. It's perfectly symmetrical. It's going to be nonpolar. If I had one lone pair, which doesn't matter where I put it because it's symmetrical, this guy ends up being polar because it's asymmetrical, right? This side, top and bottom are not the same. If I had 2 lone pairs, I'd put one on the top, and now I have a square planar shape. So this guy is symmetrical. Since it's symmetrical, all those poles are going to cancel out. So even if this is a polar bond, it's identical to this polar bond. They cancel out and it ends up being nonpolar. This guy, it's again asymmetrical, so the poles aren't going to cancel out. So this guy would again be polar. Down to here, now I've got a line, and we know lines are symmetrical. So we're back to being nonpolar. Okay, so those are all the shapes. Let's see if we have time to try a couple, or if that's the next video. Next video.